on an object is 0?
The net force. Did I say net force?
Yeah. Yep. The net force on an object is 0. Yeah. All right, the net force on an object is 0. Notice I said net force. Notice I did not say the force on an object is 0. So there usually are going to be forces still. But the net force on an object is 0. But here's another way to think about it. Another way to think about equilibrium, if the net force is 0, there is no change in motion. Okay, remember Newton's first law. Objects in motion remain in motion. Objects in rest remain at rest unless acted on by a non-zero net force. If there is no net force, if the net force is 0, there is no change in motion. So equilibrium is when you don't have a change in motion. The motion is constant. All right. I want you to think about an example here. On the back page. Number 8. A red Ferrari Barracuda is driving at a constant velocity of 50 meters per second. A brown Plymouth Duster is at rest and rusting in a garage. Which, if either or neither or both or one or what, is at equilibrium? So we said equilibrium is where the net force is 0. It's where there's no change in motion. So of those two, which one, if either or both, is at equilibrium? Take a minute and write your answer down. Number 8. So take a minute and write your answer down for 8. Neither of them are at equilibrium. Okay, why not?
Because I think that equilibrium would be things like that, like aren't objects. Like it sounds weird, but.
Cannon's trying to get metaphysical here with us in physics class. Well, Cannon, I got a good answer for you. You're not right. It's not neither. That's all right. That's a good try. It's a good try. Luke, you say both. So you also think it's a trick question. You're going with both. Why do you say both?
Because it has a constant velocity, which means the net force isn't changing on it, and since it's at rest, then
Yes. So the key to equilibrium is that the objects do not change their motion. So an object that is at a constant velocity, so this here's my super swanky sports car. See, it's got a spoiler and everything. Okay? So it's going forward at 50 meters per second. It has forces acting on it. Okay? It's got gravity pulling down. It's got a force from the engine pushing forward. There's other forces too. Like we have forces acting on it. But it's not changing its motion. Its motion is constant. And so because it's constant motion, the net force has to be 0. And the other car is at rest. Here the bumper fell off. Yep. Nope. See, the bumper fell off on this one. Also, this one doesn't have a spoiler. It's the other difference. Yeah. You can tell the difference.
Where's the rust?
Yeah, that's why the bumper's not on anymore. So the net force on this one is also 0 because it's at rest. Again, there are forces acting on it. There is a force of gravity pulling down. There's another force on it that we haven't talked about yet. We're going to talk about it next. It's called normal force. That's acting on it. There's forces acting on it, but the net force, the total force, is 0. So which is at equilibrium? They both are. They're both at equilibrium. Equilibrium is just an idea that the net force, the change, is 0. So if there is no change, the net force is 0. Again, doesn't mean there's no force. Just means that the net force is 0. Okay? All right. Jump back to the front. So what does this show? What does this picture show you about equilibrium and net force? So equilibrium and net force, what I want you to see is that a net force is 0 does not mean no force. It just means that the forces add together to get 0. So F net equals 0 does not mean...
No, we can't see it. I'm sorry.
There you go.
Thank you.
Does not mean no force. It just means F1 plus F2 plus F3 plus whatever equals 0. That's what it means. It just means that when you add all the forces together, you get 0. That's what it means. So it does not mean there's no force. It just means when you do add the forces together, you get 0. So let's look at that. Let's look at 4. I'm going to jump down here. So the net force is 0. So if the net force is 0, that means that F1, which is 100, plus F2, which is negative 70, negative because it's down, plus F3, which is negative 30 because it's down, plus F4, which is negative 50 because it's down, plus F5. When you add all those together, you should get 0. So what should F5 be? 50. The hooligans are coming back from lunch. Hooligans. 50. 100 minus 70 minus 30 minus 50 gives me 0 equals negative 50 plus F5. Well, I need to know what F5 is to give me a total value of 0, and that's going to be positive 50. God bless you. So that's what we're doing with equilibrium. We're combining forces together to figure out what does it need to be for the net force to be 0. Not that different than what I did over here, where I gave you a net force. And sometimes it was 0, but sometimes it wasn't. And you had to find what the missing values were. So not that much different than that. All right, let's wrap up here. Well, let's do one more example here. I want you to try number 7. You and LeBron James are standing in an elevator that's accelerating upwards. Your weight is 30 newtons. His weight is 450. The applied force is 800. What's the net force on the elevator? So is the elevator in equilibrium?
No.
Yes, or there are going to be 6 forces we're going to use. Okay? And those 6 forces are as follows, from most often to least often. So the one we're going to use the most often, and that's going to come up very frequently, is what's called an applied force. And I just write it as FA. It's called an applied force.
How many are we writing so much? Like
6.
no.
We're going to write 6.
No, I'm not writing that. And I just said apply force.
Yep, so FA is applied force, and it's what you do to an object.
Yeah, I'm not gonna write that.
So if you throw a baseball, that's an applied force. If you kick a soccer ball, that's an applied force. If you pull a couch, that's an applied force. The engine from a car is an applied force. Those are all applied forces. So it's what you do to an object. That's the applied force. Okay, the second force that's going to come up very often is gravity, force of gravity. And that's Fg. And that acts down from gravity pulling on you. Okay, so gravity pulls on an object down, and that's why gravity acts down. And by the way, gravity always acts down. It'll never act in any other direction. Applied force can act in any direction. You can push something down, lift something up, push something forward, pull something back. That can be in any direction. But gravity will always be down. All right, the third force is called the normal force. And no, this isn't like the most normal of forces. All the other forces are weird, but this force is normal. It means normal to the surface, which is a mathematical thing, which means 90 degrees. So normal is normal to the surface, so it's a support force that almost always works against gravity. So if you have a box, okay, if you have a box, that force that's acting upwards on the box, that's called the normal force. And it works against the gravity force that's down on it. All right. The fourth most common force you're going to see is friction.
Ooh, I know friction.
Yeah. It's a resistance force to motion or attempted motion. So it resists moving, or it resists you trying to move it. So like if I try to push a couch, but it doesn't go anywhere, that's friction. Okay? That's friction. There has to be a force keeping it from moving because I'm applying a force, so it has to move unless there's another force balancing it out. Yeah?
What's the difference between friction and inertia?
So inertia is a tendency to resist change, but it's not an actual force. So inertia doesn't keep things from moving. So right now, this wants to stay at rest, and if I push it, it's going to resist that change. But without friction, it'll move. With friction, it can stay in place because I'm applying a force and friction is applying a force back to me. Okay?
If I push a wall, is that friction?
Yes. But it's a little different because that's friction like between the... It's like friction where the wall attaches to the ground. But there will be friction holding it in place. Yeah. All right. Two more. These ones we don't use as much, so I'm going to go through them quick here. And those two are tension and drag or air resistance. Okay, tension is an applied force specifically with ropes or springs. And drag or air resistance is a resistance force through the air. So it's air friction. Okay, drag and air resistance is air friction.
So like would my hop be tension?
Because you got springs for legs?
Yeah.
Yes.